doing. I'm going to do a little demonstration, and in the handout, it'll show you exactly what we're doing. I'm doing Science 14, Unit A, Introduction to Chemicals. I'm actually just introducing them to properties of the periodic table and whatnot. In my demonstration, or in my thing, how I anticipated it, I was kind of start off the class. I'd start off by doing a review. So I'm assuming this is like lesson 3 in a sequence of a lot of things. And then, I don't care if it's running right now, but this is what my review would kind of be like. So they're learning about the periodic table. They're going to learn what kind of information is covered in it. And then it kind of just goes on. They're learning about symbols right now, and they're also learning about safekeeping. So this thing is just introducing them to safekeeping and what the symbols associated with it. And as we go on, for the higher level students, they'll be introduced to like valence electrons. And then my lesson kind of starts out here. They're learning that the periodic table is arranged according to families, and the alkali metals being the very first family. This lesson will be all about introducing them to the alkali metals. So I'm going to start off by showing you a little video. If it loads, hopefully. It's not working. Okay.
There are 6 alkali metals:
Make it full screen.
lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catching fire is burned with a light flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our thick alkali metal.
So I would have liked to show you that. I thought that the university actually carries some of these, but they don't. So I'm going to show you a little demonstration. Before I do that though, I'm going to ask you some questions through probed questioning. And I'm going to ask you some questions so that we just saw metals. I want you to kind of formulate, talk among yourselves, why do you think you can cut through these metals? What makes them unique? And why are they different than other metals? So you can talk among yourselves. And also maybe talk about why did you cut it, why did it corrode so fast as well. So kind of speculate what an alkali metal is. So talk among yourselves.
Because what it is they carry one extra valence electron on its outer shell, so it's very readily seeking to so it's very readily donating that electron. Yeah, so it's got like an outer shell, so it's got like the nucleus or whatever with all the protons in it. It's got like so depending on what element you have, it'll have like however many shells that itself wants to get here. So it'll react like.
I'm also going to let you look at some stuff going to be doing demonstrations of alkali metal compounds. So you can kind of look at them, look them up, see what their textures are. We're going to be combining them. You can kind of predict what's going to happen when we combine them as well.
So they're.
Why are they soft?
That's just sucrose. That's the So if you're doing this afterwards, they're done on plastic materials, so you can kind of predict what's going to happen when you mix them all together.
I like it. That's what I like. What they're cutting through.
Probably like the travelers. Did an extraction.
And so the reactions they are just
They're so long.
Probably the water in the
So as I was telling the other group, we're going to be mixing different alkali metal compounds because we don't have actual alkali metals. You guys can look at the compounds and kind of predict what happens. Alkali metals together over the water and base and see what we're going to actually predict what's going to happen. This is potassium permanganate, that's sodium hydroxide. Look at its textures and whatnot.
why? Yeah, the more pure they go. No, it's not in that thing, but it's
No, it's not. It's not. Yeah, it's in transition.
Yeah, I
guess. It's not. It's 11. Red number so.
Maybe
So do you guys have any predictions what happens when we mix two alkali metal solutions together?
solutions.
Yeah. What do you think about that?
Yeah.
Do you think the reaction will be exothermic or endothermic based on the video you just saw?
Exothermic.
How else have we learned so far that we learned chemical changes occur besides just exothermic? Oh, I asked how else can you observe that a chemical change occurred besides just temperature change?
Oh, color.
Color? You might
Gas.
see some color in gases.
Formation.
Okay, so hopefully we'll see some of those. You guys want to see my demonstration? If we're on a few minutes though. Alright. I would actually recommend before you actually do this, so I tested it out several times because a lot of the first few times it didn't actually work. And then I learned that in order for it to work, I had to crush it up very finely and make a little bowl. And it does stain your hands, which is why I'm wearing gloves. Yeah, it stained my hands multiple times. So you guys can actually gather around if you move if you want to. The first one I'm going to do. The first one I'm going to do, I have it prepared 3 times in case it doesn't work. It didn't work the first time because I didn't grind it up. By grinding the potassium permanganate up, I created more surface area. And then I found out that if I dumped it in and used a metal scoop to push it and make a little indentation, that the potassium permanganate will kind of absorb the glycerine and you should see the reaction hopefully. And it doesn't work. You kind of stay it up by pushing it down. I hope it works. This one doesn't work all the time. Yeah. Okay. Add some more. Okay. Okay, so that's potassium permanganate and glycerin. So what we're doing right now, before you guys predict what's happening, this is part of the observe. After the demonstration, we'll go back and explain it all. So that's the first one. So what kind of reaction just occurred?
Exothermic.
Okay, and I definitely recommend practicing that a few times. It took me 3 times to get that. My second one, I have a solution of concentrated sodium hydroxide, and I have hydrochloric acid. I'm going to combine them. What do you think will happen when I combine the two?
Form salt.
Form a solid?
Salt.
A salt?
said sodium hydroxide and
Sodium hydroxide and hydrochloric acid.
yeah.
Form a salt? Okay.
Hydrogen.
I have 50 milliliters of
It's
each.
gonna bubble. It's gonna bubble.
We're all gonna die.
It's gonna bubble lots.
Let's find out if it bubble lots.
I want it to. Yeah.
Okay, and you guys can pass this one around because this one is not too hot, but it definitely did release a lot of heat.
Oh yeah, that's warm.
So that's another form of exothermic reaction. I'll wait till that one goes around because the last one's really, really cool. You guys can touch the bottom if you want. It's not too hot. Yeah, so before everything was at room temperature, I just created it before to save time. And here I have a solution, it's just water and a little bit of potassium permanganate. In here I have a little bit of sodium hydroxide and some sugar and water. What do you think will happen when I combine them?
So what's in that?
Potassium permanganate and sodium hydroxide.
Color changes.
So it's like two alkali metals meeting. What do you think will happen?
An explosion.
Explosion?
Fire again.
I hope it's fire again. I hope this one works. Okay, so it's going to change color multiple times. It went from purple. It's now green. It's going to change to yellow.
Oh, there it goes.
Yeah. And then if you let it sit, eventually it'll turn back to clear.
Cool.
Yeah. So afterwards we'd explain exactly what went on, but this is just to perk their interest what an alkali metal is and how they're different, what makes them unique. Yeah. How am I for time?
3 minutes.
Okay, so you guys want to have a seat? I just prepped everything before because I don't want to measure stuff out, and I thought it would be a bit easier. Constructive feedback. Yeah.
The lab activity is cool. Anytime you have an explosion, kids are always going to be intrigued and will want to know how that happened. So obviously they can go do it
That's
at
the only
home.
reason I picked it too, actually. Any other comments?
Why can you cut those metals?
Yeah.
Oh, because well, the alkali metals, they actually have one extra valence electron, and that makes them very unique. And because they have that extra valence electron, it also explains why they actually readily want to react. Because they only have one extra electron, they usually want to donate it. So each outside shell can have 8 electrons. They can either gain 7 electrons or donate 1. It's easier to donate 1, which is why they're very reactive with water and air. And because they're so reactive, you can't even store them in the lab, which is why I opted for a different thing.
Why they solve.
Yeah. It also explains why they corrode very easily as well. Any other questions? Yeah.
So how would you go about explaining the color change we observed in the third?
I would just ask the students because I'm just introducing them to what chemical changes are. So I would actually have them like fill out a little sheet and observe what they noticed. And then when we got back to class, I'll be like, so a chemical reaction occurred. What did you notice before? Why do you think it occurred? Was it exothermic in nature, endothermic? So they kind of predict what happens, and they try to explain it themselves. Yeah. Anything else?
I thought it was good to show the video ahead of time because I know when I was teaching, there were kids that would get really upset if you just did if there would be an explosion or fire. So they need to be prepared ahead of time.
Yeah, that's like kind of wanted to like have you. A lot of people predicted explosions each time, so I wish it was, but I thought it was good to show different reactions too that could occur as well. Each one kind of had a different product or whatnot. I actually have like a detailed procedure if you want to do it. It doesn't take that long to set up at all. Anything else? Was my pacing okay? All right. Hey.